thanks very much to the EarthByte group for hosting me, and particularly for Salvin. Been extremely generous with your time, and yeah, you guys have a really dynamic, exciting group. It's been quite inspiring to be here for a couple of days, so thank you. Before I get going, I'd also like to acknowledge the traditional owners of the land which I work and spend most of my time, which is the Wurundjeri people of the Kulin Nation, as well as the traditional owners of where we're meeting today in person at the University of Sydney, which are the Gadigal people of the Eora Nation. So as Salvin said, I'm a research fellow in tectonics and thermochronology, and I split my time between the University of Melbourne, where I help lead the Melbourne Thermochronology Research Group on behalf of its founders, Emeritus Professors Barry Conn and Andy Gledo. And the other half of my time, or at least since July last year, is working at the University of Adelaide, where I work particularly closely with Stein Glory, Alan Collins, Morgan Blades, and Angus Nixon from the Tectonics and Earth and Systems group. Today, I'll primarily be talking about continental rift systems, and in particular, how the thermal evolution of the upper crust, as constrained by thermochronology techniques, can tell us more about how these systems evolve, the mechanisms that govern where they form, how they form, and how we can glean some insights into these inception processes. So as you're all well aware, continental rifting plays a critical role in plate tectonic theory, thinning and stretching the continental lithosphere forming basins in these subsiding regions. If successful in rupturing continental lithosphere, they create new ocean basins, dispersing continents. And this has the net effect of affecting many of the dynamic systems of Earth. The development of continental rifts are intrinsically linked to mantle dynamics, but also can have an effect on the way that the thermal and convective state of the mantle can evolve over time, particularly in the upper ionosphere. Many, not all, but many rifts are also associated with quite significant volumes of extrusive volcanics. And this, combined with outgassing along fault systems, pour lots of volatiles and greenhouse gases into the atmosphere, changing its composition in the process. Volcanic buildup, dynamic topography, the formation of rift basins, uplifting rift margins, the formation of basins. These have huge ramifications for the evolution of the surface of the regions that are undergoing extension. And this in turn can change this in turn can affect the way in which our atmosphere circulates and can affect climate through orographic rainfall patterns and things like that. If successful in rupturing continents, the successful rifts increase the length of coastal margins, creating new habitats for life in shallow marine environments and coastal terrestrial environments. They can isolate continental fragments, isolating particular creatures and driving speciation, such as the lemurs of Madagascar during the breakup of Gondwana. Continental rifting in East Africa in particular has been pointed as a potential driver for speciation in our hominid ancestors, essentially creating new isolated environments that may have driven adaptation. And of course, rift environments today still dictate the lives of many hundreds of millions of people around the Earth, such as these guys from northern Kenya. So despite the importance of these systems for many aspects of Earth's dynamic systems, there's still fundamental questions regarding the relative role of far-field stresses from predominantly slab pool versus things like plume activity in driving rifting, stenospheric upwelling and associated dynamic topography, or basal traction at the base of the lithosphere. There's also, I guess, questions remaining or variant opinions about the relative importance of associated magmatism for lowering yield strength of the crust in particular, and helping to nucleate brittle strain in the and there's also questions regarding the role of inherited zones of weakness in the lithosphere for nucleating strain. Numerical and analog models have shown that, for instance, areas of pre-existing weakness in the lower crust or mantle lithosphere can help nucleate brittle strain in the upper crust in those regions above those weak zones. And other people have also suggested that these are playing important roles on much larger continental scales. For instance, certain people pointing out the correlation between the distribution of extensional basins in the African rift system and their correspondence to Proterozoic mobile belts and suture zones that formed during Gondwana amalgamation, for instance. So one of the best places in the world to start to investigate some of these fundamental questions about how continental rifts form is the Afro-Arabian rift system. It's the largest continental rift system on Earth today, encompassing the Red Sea and Gulf of Aden systems, and extending pretty much the full length of the African continent, including the East African rifts, its eastern, older, magma-rich branch, its generally younger amagmatic western branch, and quite young, incipient rift branches in the southwest. Because of its age and complexity, it really encompasses the full spectrum of rift development, from incipient rifting in the Okavango Rift, which is less than 100,000 years old, to quite mature series of half-graben basins like you find in the Kenya segment, for instance, of the East African rifts, to incipient oceanization in the Afar Triangle, where you have subaerial oceanic crust forming, to successful lithospheric rupture and the formation of new ocean basins, such as in the Red Sea and Gulf of Aden, where we've had seafloor spreading for at least the last 13 million years. So why is East Africa rifting today? Well, interestingly, the African plate is surrounded on three sides, essentially, by mid-oceanic ridges. And to the north, the plate's in a state of compression as it collides with Eurasia. Yet nevertheless, while we might expect that Africa should be in a state of regional compression, it's under extension. And that's because the Afro-Arabian rift system is formed diachronously above the so-called African superplume, this large low shear wave velocity province that's emanating from the core mantle boundary beneath southern Africa and impinging beneath the East African and Arabian crust. Some people have pointed or suggested that perhaps basal traction due to convecting ascenosphere at the base of the lithosphere alone could account for modern extensional or deviatoric stresses. However, other people point to the role of essentially significant amounts of volcanism over the life of this rift system, perhaps today most spectacularly at Mount Nyiragongo in the eastern DRC, which is the world's largest lava lake. And this long history of rift-related volcanism since the Eocene has resulted in the extrusion of huge volumes of lava at the surface. In places such as the Ethiopian Plateau, shown here in the Simien Mountains, these obtain quite significant thicknesses of well over a kilometer. So these additions to the I guess top of the crust, as well as poorly quantified, but no doubt significant contributions through magmatic underplating and the intrusion of plutonic bodies into the lithosphere, plus a significant dynamic topography component due to this impinging plume, has created this large region of residual topography, collectively termed the African superswell. And people like Sarah Stamps and others have formed calculations where they've determined what the gravitational potential energy of the African superswell is, and what the predicted deviatoric stresses from that gravitational potential energy component alone, what that stress field looks like. And it actually matches the modern day kinematics of the Afro-Arabian rift system remarkably well. Their work also suggests that those deviatoric stresses alone from the essentially gravitational collapse of the African superswell, are sufficient enough to continue to drive modern rifting, but importantly, that they're insufficient to rupture cold, thick lithosphere. So other processes must have been at play at the onset of the Afro-Arabian Rift system in the Paleogene. So despite much of our understanding of continental rift processes coming from many decades of work being done in this region, some fundamental questions remain as to what geodynamic and/or tectonic mechanisms was driving rift inception in the Paleogene, which mechanisms controlled where rifting started to form, and what are the relative roles that far-field stresses at the plate margins, plume dynamics, and then gravitational collapse of anomalously high topography play in rift onset. And essentially, to address any of these questions, we must first better our understanding of really what the detailed spatiotemporal chronology of rift development was. Where did rifting begin? How did it propagate subsequently? And so one of the tools that we have at our disposal to do this are a series of temperature-sensitive radiometric dating techniques called low-temperature thermochronology. Like any radiometric dating technique, they're based on the radioactive decay of some parent nuclide to a daughter nuclide. And like all radiometric dating techniques, the retention of that daughter product is temperature sensitive. The difference for low-temperature thermochronometers is that the sensitivity range, I suppose, of when that system remains open, when we're actually still diffusing the daughter nuclei out of the crystal lattice, that temperature sensitivity overlaps processes that are happening in the upper crust. So that allows us to take advantage of these natural phenomena and start to determine or constrain the timing and rate of thermal events that happen in temperatures that we find often in the upper crust. In particular, today I'll be talking about fission track and uranium, thorium, helium thermochronology. And generally we apply these, or most commonly we apply these to the mineral systems zircon and apatite. And that's because, one, we find apatite and zircon in quite a wide range of lithologies. So we can use them in most geological settings. But also importantly, their temperature sensitivities correspond with things that are happening in the upper crust. Sedimentary basin formation, zeolite facies metamorphism, the growth of topography, and surface processes. I'll take a minute just to talk a little bit in detail about how the fission track system works, just to show better how we can really take advantage of the systematics of these thermochronometers to constrain thermal evolution of rocks. So fission track system is based on the decay of uranium-238 atoms by spontaneous fission. And when this occurs, essentially the uranium atom undergoes spontaneous fission. Generally, two subequal nuclides fire off in complete opposite directions at extremely high energies and essentially strip ionic bonds and kinetically interact with other atoms in the crystal lattice and leaving this linear damage trail in its wake, which we call the fission track. And we can then chemically etch them and enlarge them so that we can see them under an optical microscope. And each one of these little fission tracks here shown in the mineral apatite records an individual atomic event, which is quite spectacular to think about. But it turns out that the retention of these fission tracks, like the daughter product for all thermochronology techniques, is temperature sensitive. So in a minute, or in a second, I'll play a little animation. On the right-hand side, we have the time temperature plot. You've got temperature increasing downwards. You can't see, at least here, you can't see the time axis is the x-axis, increasing to the left. So essentially, modern day, present day temperatures of the modern day sit somewhere in this upper right corner of this plot. And in a second, when I press play, a time temperature path will begin forming, starting at higher temperatures in deep time at some point in its bottom left corner. And what we'll see is that when this mineral illustrated here, say it's an apatite crystal, when it's at temperatures above some temperature sensitivity range, these fission tracks, essentially because there's enough energy in the system because of the thermal state of the rock, which which this crystal is a part of, that these fission tracks thermally anneal and essentially instantly heal relative to geological timescales. And it's only once that sample cools within some temperature sensitivity range that we start to partially retain these fission tracks. They shorten, but to a length that's proportional to that individual track's, or to the temperature that individual track has experienced. And then at low temperatures, we retain the full length. So we start seeing these fission tracks forming at some set known rate, and only once this rock or this sample cools into the temperature sensitive range, we start to partially retain these fission tracks, although they shorten slightly, and then at low temperatures, we retain the full length. So to take advantage of this, we can essentially quantify how many of these fission events have happened literally by performing digital microscopy, counting how many fission events we see in some two-dimensional surface. We can measure the parent nuclide concentration, so uranium-238, via laser ablation mass spectrometry. And we combine those two elements and using the known half-life of spontaneous fission in uranium-238, we can determine a fission track. But importantly, we can also look at the distribution of lengths of these individual tracks. As I mentioned, each individual track, it's a singular atomic event, and the length that it records, I should say that these always form at the same length initially, but the length that they retain is proportional to the temperature, the highest temperature that individual track has experienced. So if we look at a distribution of many of these tracks that are formed at different times in the life cycle of this mineral, we get some distribution, and we can combine both of those information, both the age and the track length distribution. We can then do numerical modeling to determine what's the most probable time temperature history that mineral has experienced to produce that fission track age and that length distribution. And then we can also throw other types of thermochronometer data into the simulations, further constraining the temperature space, essentially time temperature space in that thermal. So how do we use these to constrain geological processes? Well, in certain instances, these could have the potential to to help constrain the timing and rate of any change in the thermal regime of the crust. In certain circumstances, that can tell us about change in geotherm or isotherms due to activity and the emplacement of plutonic bodies in the crust, or changes in temperature regime due to hydrothermal fluid flow or groundwater flow, and sometimes about the formation of particular mineral deposits associated with these. But in general, these sorts of data we find tell us more about the advection of mass and heat towards the surface in response to denudation and erosion and/or exhumation. So this can tell us about passive erosion that's happening due to differences in topography. They can also tell us about tectonic exhumation and associated. For instance, in extensional settings, the uplift, exhumation, and then therefore and subsequent erosion of footwalls of large basin-bounding normal faults, whereas analyses of syn rift strata can tell us about burial associated with basin formation. And the converse is true in compressional settings, where you'd have advection of the upward advection of the hanging wall of generally lower angle thrust faults. But today, we're particularly interested in passive erosion and normal faulting in the context of extensional settings. So one of the conventional ways in which we apply this in rift settings is as a technique to constrain the age of basins by looking at the thermal evolution of rift margins, namely the footwalls of basin-bounding normal faults, such as this example from northern Kenya. And you then collect samples along strike of the basin-bounding normal fault, as well as orthogonal or suborthogonal to that fault trace into the footwall. And if we look at this in a 2D cross section and projecting these samples onto a seismic line, we have a series of, we'd go in the field, make some structural observations, geological observations, collect our rock samples in this pseudo transect through the footwall of the basin-bounding of the footwall of the basement mounting fault. Go back to the lab, produce a bunch of fission track engineering from helium data, and then run inverse, or in some cases forward numerical modeling simulations to simulate the thermal history that these rocks record. And in this instance, these systems actually recorded some of the higher temperature systems. We applied zircon helium, apatite fission track, apatite helium. So we actually got quite a long, rich thermal history that these samples recorded. But in particular, we're interested in the formation of this modern Miocene rift, which the thermal history models combined with seismic data and well data, we suggested was, we constrained the formation age to be about 13 million years old. So that's an example of how we can use these data to constrain the age of basins. It also turns out that in certain circumstances, a long strike differences in the thermal evolution of rifted margins can also tell us about how these big normal fault systems have evolved. So here we have two kind of simplified end-member normal fault system evolution models. On the bottom, we have the constant length model. And this model suggests that in certain circumstances, faults can grow really rapidly, attaining much of their length quite early in their history, and then later accommodating more displacement over time. And by that model, we'd expect that along strike, the rocks in that footwall would all have about a similar coeval onset of cooling associated with footwall uplift, and that you'd have kind of this sort of pattern, a predicted pattern seen in the bottom right three cooling versus time plots. Whereas the other end member normal fault growth model is called the segment growth and linkage model, where you have a number of initially isolated fault segments. Here we're just showing two in that top left plot that are both propagating laterally and accumulating displacement as these faults grow. And eventually these faults start to interact to form a relay ramp that's eventually breached, and you get a hard linkage between these rift segments, and then it forms a much larger normal fault system. And here we would expect that areas within those initially isolated faults start cooling as those faults continue to grow and their footwalls continue to be exhumed and erode. And those areas that were initially in between those isolated fault systems are thermally stable until those fault systems link, and that once under displaced portion of this now much larger fault, as it starts to accumulate really rapidly displacement, and the footwall in association then starts to exhume rapidly, we then see a later onset of cooling in that interim region and much more rapid state of cooling. So let's talk about some work that's been done by my colleagues and I and many others in the Afro-Arabian Rift system, applying thermochronology to better understand how this system has evolved. So we were interested in trying to better understand when did Afro-Arabian Rift system first initiate. And the region that we targeted is called the Turkana Depression. It's a low-lying area between the Ethiopian Dome to the north and the East African Dome to the south. Here, the earliest manifestation of rift-related volcanism is found, called the Amorogamo basalts that began erupting around 45 million years ago in southern Ethiopia. And there's also already evidence to suggest that some of the oldest, if not the oldest, rift basins in the entire system were found here. One in particular that we're interested in is called the so-called Lokichar Basin, an exploration well that penetrated the basin along its flexural margin of this half-graben system, penetrated Oligocene synrift strata, but the deepest, earliest synrift strata in the system basically remained unpenetrated at depth. So we knew that it was at least Oligocene or late Oligocene in age, but we weren't quite sure really how old this system was. In addition to its antiquity, the Turkana segment of the rift is anomalous in other ways. Unlike the more narrow rift segments to the north and south, such as this, in the image at the bottom here from the central Kenyan rift, we have quite narrow rift basins, 50 to 70 kilometers or so wide, that traverse these topographic highs, and you get this really kind of typical uplifted margin, down-thrown basin morphology. But in Jacana, in the image in the north, we have very little topography, actually, and the only thing that's kind of sticking out from these expansive thicknesses of sediment are volcanic mounds, essentially, and occasionally the nose of these big basin faults. The crust is also very thin here. It's about 20 kilometers thick, according to seismic fraction data, compared to much thicker crust, about 35 kilometers or so beneath the Kenyan Dome and Ethiopian Dome to the north. And people have attributed this anomalous behavior of the Jacana segment of the rift to tectonic inheritance, essentially, that suggesting that two older Cretaceous early Paleogene rifts once connected in this region, the Anza Rift, which is preserved in eastern Kenya, South Sudanese rifts to the northwest. Unfortunately, if these rifts did indeed connect, I guess direct evidence of that connection is poorly preserved, perhaps due to subsequent rifting dissection, and then also the extrusion of the huge volumes of volcanism obscuring what's in the subsurface. So we went to the Lucky Char Basin, we collected samples from its footwall as well as its flexural margin. And what we found is that in this plot shown here, that areas in the proximal footwall of the Lucky Char Fault, we produce much younger fission track and apatite helium ages compared to the more distal regions away from the fault trace, where these preserved older late Cretaceous ages and Paleogene ages that correspond to kind of the regional background thermochronology of the region. And thermal history models show a similar pattern where the proximal fault region experience, in contrast to these more distal areas that have just kind of monotonic cooling, at least as reported by these since the late Cretaceous. Excuse me. These more proximal areas started experiencing really rapid cooling sometime between about 35 and 45 million years ago. And we combining that with seismic data and well data from within the basin, we suggested that this is consistent with the Lucky Char Basin being possibly as old as the late Eocene. We did this for a number of basins in the region, and combining our findings with data, all types of data from previous work in the region, shown here in this chronogram, dark solid blue blocks corresponding to areas where we have I guess hard dates, either through biostratigraphy or geochronology, of how old synrift sediment are. And these dashed lines are basically earlier periods of potential basin formation that people have suggested based on primarily remote sensing data, but which we had hard data lacking. And we combined our findings with other thermochronology studies in the region. And what we found is that we have a general eastward propagation of brittle deformation in the Jacana region over time since the Eocene. And from this early nucleation point in the Lucky Char Basin area, we also have latitudinal propagation of rifting both north and south from this initial nucleation zone. Zooming out and combining it with lots and lots of work done by lots and lots of scientists over the last 100 years or so, from the entire Afro-Arabian Rift system, the chronology that we're starting to discern is that we have these distinct nucleation points in the system. One in the Jacana Depression, is possibly as old as the Eocene. Certainly, we're confident that we're extruding volcanics by 45 million years ago. And then in the far, we start seeing plume volcanism and basin formation in the Oligocene, and as well down in the south in the so-called Rukwa Rift, we start getting both volcanism and extension in the Eocene. Oligocene. And then you have subsequent kind of latitudinal propagation from these discrete nucleation zones And by the Pliocene, certainly latest Miocene, we formed a nearly continuous rift system spanning much of the length of the African continent. How about the role of tectonic inheritance? Well, we can get some insights in the role of pre-existing lithospheric heterogeneities from southern Ethiopia in the so-called broadly rifted zone, where you have a number of basins kind of stacked west to east, basically at the northern margin of the Chakana Depression. We looked at two different basins, one on the western extent of the broadly rifted zone called the Beto Basin, and looked at another basin in the east called the Galana Basin. And what we find is in the Beto Basin, it has quite a distinct architecture. The basin trends northeast, southwest. The major basin bounding fault in this half graben on its northwestern margin has this distinct zigzag pattern. And you can see that in the Rose diagram there. And that corresponds quite neatly with two overprinting metamorphic fabrics that you see throughout the Proterozoic basement rocks in which this basin formed, suggesting perhaps reactivation of this pre-existing metamorphic fabric. And the thermal evolution of the margin is consistent with what we might expect for the segment growth and linkage model, where we suggest that you would have had a number of smaller and initially isolated fault segments that developed parallel to this regional discrete metamorphic fabric in the rocks in which the basin formed, and that these things propagated over time and linked together, forming these larger fault systems that accommodated subsidence in their hanging walls in the formation of these basins. To the east, in the Galana Basin, we see very different architecture. The basins trend north-south, they're much longer, and the faults are almost entirely broadly north-south trending. And here we see that the thermal history models, albeit our spread in data was limited, unfortunately, we were unable to get to the southern part of the Galana Basin. But at least in the transects that we had, it suggested that its footwall, so-called Amara Horst, recorded a thermal evolution that is consistent with what we might expect for the constant length model, where suggesting that these faults, these arcuate long, uninterrupted faults perhaps grew quite rapidly or propagated laterally quite rapidly, only accumulating displacement later in their lives. Why do we care? Well, what's interesting is that despite those kind of overprinting northwest and northeast trending metamorphic fabrics that we see throughout the Proterozoic rocks of southern Ethiopia, something's happening in the eastern part of the broadly rifted zone in the so-called where the Galana Basin is formed to kind of override the influence of that. And we suggested, pointing to work of Karen and Klemper and others, which use seismic tomography to essentially image this really large step in the lithosphere thickness that underneath the Galana Basin and the main Ethiopian rift above it. You can see their model on the left-hand side here, rotated, so it kind of orients similar to those maps. And so we suggested that perhaps this large, and I should also mention that that large step in lithospheric thickness between the Nubian plate to the west and the Somali plate to the east is thought to correspond to a major Proterozoic suture zone that formed during the amalgamation of Gondwana. So we suggested that the influence of this lithospheric scale pervasive fabric kind of overrode the influence of the, I guess, more discrete metamorphic fabric in the rocks outcropping at the surface. Unfortunately, we don't have as nearly as good of understanding of the Proterozoic basement further south in Chakana proper, where we think rifting first nucleated. But we're hoping that's going to change. Last year, we started a project working with Alan Collins, or I started a project working with Alan Collins and Morgan Blades at Adelaide, where we're doing just that. We're going to do essentially a lot of the fundamental work to better characterize the Proterozoic tectonic history and lithologies that are preserved in northern Kenya. So stay tuned. We're doing, in addition to making lots of structural measurements, we've brought lots of rocks back to Australia to geochemically and geochronologically characterize. So zooming out again quickly on nucleation mechanisms, or the role of nucleation mechanisms on a entire rift system scale, and looking at these three discrete nucleation points in the Afar region at the kind of the triple junction where the Gulf of Aden, Red Sea. Rifting there is thought to be driven predominantly by slab pool due to subduction of the northern margin of the Tethys in the Oligocene. And strain is thought to have been nucleated by the impingement of the Afar. People have done, like Belason and all have done some analog modeling work. There's lots of people that have done numerical modeling work as well to suggest that indeed that plume impingement would have been sufficient enough to lower yield stress in that region. In the Rukl Rift, I think we're less certain what was driving rifting in the Oligocene, but there is a clear correspondence between the location of those rift basins and a mesoproterozoic mobile belt called the Ubendian belt, which essentially is a suture that formed during the amalgamation of the Tanzanian craton, Archean Tanzanian craton to the north and the Kopfall craton to the south. So it suggests that there's an influence of these, again, pre-existing lithospheric heterogeneities in that Rukl sector. In Chakana, it's perhaps that both mechanisms are at play. As I mentioned, it appears at least in southern Ethiopia, there's certainly a role of these pre-existing Proterozoic basement fabrics and lithospheric architecture that are playing a role. Assuming that these Cretaceous systems did once link Chakana, people like Ebinger and Sleep and others have suggested that this area of pre-attenuated lithosphere could have acted as a way of essentially nucleating asthenospheric upwelling beneath this region, which they use to explain why the earliest plume-related magmatism that we find is in this southern Ethiopia area. That, of course, could also lower the yield strength yield stress. And others have also suggested that there's some correspondence between some topographic features and geomorphological features in Chakana that have a kind of broadly northwest-southeast trend, perhaps suggesting that if these systems did truly connect in the region back in the Cretaceous, that some of those structures may have been reactive. What was driving rifting, however, is more enigmatic. So as I mentioned earlier, I suppose the consensus or predominant consensus at the moment is that modern extension is being driven by gravitational collapse, predominantly of the African superswell. However, we don't have evidence of the African superswell prior to the Miocene. I guess a caveat being that paleoaltimetry is an extremely, difficult quest in geology. It's difficult to constrain past topography. So it could simply be that we just don't have earlier evidence for it. But even if there was domal topography associated with this initial plume impingement Miocene, numerical models by Burov and Guria suggests that we would expect to actually see these kind of concentric circular basins forming due to gravitational collapse. We don't see this in nature, obviously. One reason is because these things aren't happening in a vacuum. There's pre-existing rheological and lithological structures in the lithosphere that can help guide the stress field. But another way to orient basins north-south in the way that they are preserved in Chakana is if there was an existing far-field extensional stress field at that time. Interestingly, in the Paleogene, we also see some reactivation of certain basins in the Eastern Anza Rift and that Northwest South Sudanese Rift, suggesting that this is a regional extensional stress field. So perhaps, this is just to say that perhaps far-field stress has played more of an important role back in the Eocene. And what's happening at the plate margins at the time? Well, Rosenbaum and others suggest that there's a plate reorganization in the Mid-Eocene in the Eurasian and Iberian plates to the northern margin of Africa at that time. And on Africa's eastern the African Plate's eastern margin, Andy and others record quite an abrupt change in extension directions in the Indian Ocean ridge at around, I think it's the 200, Pron 200, which I think is like 42.8 million years or something like that. This is just to say that we think that there's evidence to encourage people to look at the potential effects of far-field stresses, what's happening at the plate margins, and could these have played a role in rift inception in Eastern Africa. I'll end very quickly into talking about some of the work we've been doing more recently and how I think there's some really interesting and exciting things on the horizon about how we can better integrate these really large thermochronology data sets with other numerical to test some of these hypotheses. Some of the work I'm about to show is work that I was involved in as part of the Oscope geochemistry network, as Salvin mentioned. Initially, this involved, well, it's always been a very large team of geochemists from across Australia, initially based at Curtin University, Macquarie, and Melbourne, and working with Oscope, and really critically also working with geospatial data company Lithodat, also based in Melbourne. Very fortunately, we're actually continuing to grow. Last year, we've added 8 more institutions as part of the AGN team, and 9 really talented geoscientists as well. So it's a really exciting group to get to work with. I guess our main project has been developing the so-called OzGeoChem data platform, which we published last year. And it's open access for people from all over the world to use. And it allows people to both archive and disseminate their data, but more importantly, I think, geospatially interrogate your data. And as part of this work, we formed what we call the Low Temperature Thermochronology Expert Advisory Group, which I had the pleasure of leading, that included Renji Zhou from UQ, Fabian Coleman from Lithodat, and myself from Melbourne, Stein Glory from Adelaide, and Mark Danzig from Curtin. And we focused on building a thermochronology extension to the platform for fission track and uranium thorium helium analyses, which have a number of data, I guess, method-specific data analysis functionalities, such as producing interesting heat maps and things like that, looking at the relation of data, of thermochronology data and topography through some interesting swath profile tools and things. This is currently in review, but you can see a preprint at Earth Archive, and these tools are already functioning in OzGeoChem. So I encourage you to go have a play. I think the really exciting thing, though, in addition to getting to look at large amounts of data and interrogate them, I think the most important ramifications are yet to come, and that is simply because in order to store data in a relational database, you have to clean it and store it in a structured, organized way. And what that means is that we can then take advantage of OzGeoChem's open API, to then make calls to the database and pull out all of this data quite rapidly and then integrate them with other numerical techniques. As an example of the potential of what we can do with this, in 2021, we published a paper in our Science Reviews looking at all the thermochronology data from the Red Sea, Gulf of Aden, and Arabian region, and we produced time-integrated cooling heating maps for the region. We could then take those data quite readily and then start putting them into plate tectonic reconstructions. And I think there's 2 major take-homes here. One, we saw that, as I suppose we expected, that regions of really pronounced cooling, such as like in this top right panel at 23 million years ago, we see on a regional scale, limited of course by the spread in your data, but that we get periods of really pronounced cooling on the incipient margins, as for instance we have at the timing of rift initiation. And areas of reheating as recorded by burial history models from well data, for instance, as we of course expect in within the basins at those times. But I think another perhaps more exciting take home from this is that it suggests that regional thermochronology data could provide a really valuable tool set for validating plate tectonic reconstructions in areas where we don't have the oceanic crust preserved, and that there's a lot more uncertainty involved with those tectonic reconstructions. So I'll end here, but I just wanted to, thanks again very much for your time and attention, and take any questions.